I have a total of 17 slides in both of these parts. And then actually I'm going to end with kind of taking a look at the constellation Orion. But I kind of feel this is actually a deja vu slide. You're like, this is so deja vu. And it is. Dark matter. And it's on the slide. In our galaxy, where is the dark matter located? I'll give you a hint. This is the disk. And then what the halo region exactly. And so there's a test question on there, something kind of like this. Which of these lines, well, it says, which of these lines represents how stars orbit our center of our galaxy? Remember the way this works is, this is the center of our galaxy, we're getting farther and farther and farther away. What do stars do that was unexpected with regard to their orbit? They move faster than we thought they should be. You guys told me Jupiter moves more slowly, and it does, because it's farther from the center of mass here. But we go out, and an analogous star that's in Jupiter's position moves really fast. And the reason it can do that is because there's dark matter that's actually distributed in the halo region, making that happen. So this is a slide, this is similar to the slide we looked at before. Yep, the red line is the observed. It goes faster than it should, and this blue line is what Kepler said it should happen. Actually, Kepler's laws, planetary motion, also Newton said it like that too. Okay, so I just want to take a quick look at dark matter. Well, actually, the thing I want to look at dark matter is this phenomenon called gravitational lensing. Now, I don't know if you remember, but one of the videos we watched showed a guy that was blowing glass, and you can make all sorts of different shapes, and he ended up making like a plate, and he took that thing of glass and he kind of went like this, and what happened to the image we were looking at as you took that plate of glass? It distorted it, yeah, it kind of made it wavy. And that's actually what eyeglasses do. They take the light and they refract it or bend it, and then the image looks different through a lens. And so one of the things we talked about was, like this slide says, Einstein said that as you're walking around in space, you're walking around in space, which is space, but there's also a time component. So we have kind of the fabric of space and time. And we talked about actually how objects, the more dense they are, the bigger dent they make, but objects on the fabric of space and time make a dent. So here we have a galaxy that is pretty massive, pretty dense, especially a supermassive black hole in the center of it. And it could be a cluster of galaxies. And it has dark matter in the cluster of galaxies. But what it's doing is making a dent on the fabric of space and time. Now, we didn't talk about this energetic event. I don't think we will. I think I pulled it this semester. But a quasar is just a very energetic event, oftentimes associated, they think, with the formation of a black hole. Black holes form from various reasons, but the biggest one we talked about was the supernova type 2. So we have this very energetic event out here, and can you see the light from this very energetic event? Okay, it's being bent by this dark matter right here. It's converging. Okay, it's being lensed. Well, here we are over here on Earth, okay, and we can see the galaxy, and as it turns out, the bending of this light, it would go this way, but it's being bent this way. So this is the normal trajectory. It's bent because of the presence of this object on space and time. And so actually to us, it looks like this quasar is here, but it's really here. And again, it's kind of like when you take the lens and you kind of look at objects, you're like, well, it looks like it's here, but it's really here. So with gravitational lensing, we actually can see double images of an object. So this object behind the galaxy, probably couldn't see it because it's in line, we actually see a double image of it. It's weird. It is weird. And we've already kind of looked at this before. So what you're looking at here is gravitational lensing, and you have to kind of know what you're looking at. The blue kind of wispy things is the object beyond the object that's doing the lensing. The object that's doing the lensing happens to be this cluster of stars. Is this the Able? No, it doesn't say. clustered stars. So it's gravitational lensing an object in the distance. More gravitational lensing, and it kind of almost looks like something got looks like frankly roadkill. Yep, I'm sorry, but that's what it looks like. Roadkill is quite disturbing. So, but that kind of image there is kind of the image of the light that's beyond the thing that's doing gravitational lensing. That's being, and just like lenses can magnify, we can get this magnification of the fabric of space and time being warped by this galaxy cluster. Gravitational lensing. Beautiful. All right, on to part 7. I told you it's short. Evolution of galaxies. So what you're looking at here is kind of think of we are over here, and we're kind of we have our telescope set up, and these are nearby galaxies. These are getting a little more distant, and these are getting even more distant. Now, I think I asked this the other day. What do you think? And I'll kind of ask this so we'll go one of 2 ways. So these guys back here are farthest from us. So how many people think that these must be very kind of young after the Big Bang happened? They're very young galaxies. Me too. I think they're very young galaxies. The farther away the galaxy is, the longer the light had to take to get to us. So that means that we're looking at a really baby picture. Look at it this way. These nearby galaxies, like Andromeda, 2.2 million light years away. Okay, it only had to take 2.2 million years to get to us. So those aren't very old pictures. Okay, these guys back here, we're talking, I don't know, 13 billion with a B light years away. So it took 13 billion years for that light to get to us. So we're looking at it as it was 13 billion years ago. Okay, so anyway. So what this figure does is it has, down here is not distance, but down here is time after the Big Bang. So here we have about 2 billion years after the Big Bang, 4 billion years, 6 billion years, 8 billion years, 10 billion years, 12 billion years, 14 billion years. Okay, so actually we kind of date the Big Bang as occurring maybe, I think the latest was 13.6 or so billion years ago. So that's what we see. And so I want to take a look. One of the things that's on your test is, which one looks more ordered to you? Do these old ones look prettier ordered, or do these newer ones look? Now, wait a minute. See, I'm saying I just said that backwards. These are young ones. Do these young ones look pretty, or do these old ones look pretty? Well, a mother would say they both look pretty, but I'm thinking the old ones look prettier. And that's actually, there's some reasons for kind of these disturbed shapes. Over here, what's that?
I mean,
so we talked about proto this, proto that, right? A proto star was a star that wasn't quite done yet, right? Proto galaxy is one of the things I want to talk about now. We can talk about galaxies forming from this proto-galactic cloud. Do you see the word galaxy in proto-galactic? Proto-galactic cloud. A cloud that's going to form a galaxy, proto-galactic cloud. What do you think? Proto-galactic clouds need to be bigger than a giant molecular cloud? Yeah. Okay. So one of the things I'm going to kind of talk you through, and it's on the test, is how do we form these there's 4 actually types of galaxies. Can you tell me 4 types of galaxies? Spiral, barred spiral, elliptical, irregular. Ooh, awesome. Exactly. I want to take just a minute to talk about spirals and barred spirals kind of being collectively the same, and ellipticals. So with a protogalactic cloud, I wonder if it didn't, oh, no, okay, it's 2 slides from now. I got ahead of myself. Very good, by the way. So this is kind of a neat sort of it starts in the upper left-hand corner, goes to the lower right-hand corner. Can you guys see these 3 boxes? Think of those 3 boxes. The one thing that's wrong with those 3 boxes is they should be expanding because the space and time actually expands over time. But this could be our universe. And so we kind of have, it's not uniform because if it was uniform, stars would not form, galaxies would not form, planets would not form. But there's a bit of non-uniformity to it. We'll talk more about that in Unit 5. And those non-uniformity form those little knots, and these little knots right here are not stars, these little knots are galaxies. Starts with the letter V, galaxies are around big empty areas called voids. Very good. Yep. So this is kind of showing you over time how these protogalactic clouds can kind of get stimulated and condense and ultimately become the galaxies we all know and love. Although the first galaxies were very kind of disturbed looking. This is where I thought we were. I want to kind of talk you through the whole elliptical versus spiral. So hopefully you guys can see this down here. I like pictures, I like figures. So what sort of galaxy does this one look like? A spiral. Yep, it could be a spiral or a barred spiral for now. What do you think about this one? Elliptical, yep. So what this is kind of saying is that if we had rotation, or if there was rotation in that protogalactic cloud, it would tend to give us a spiral. No rotation tends to kind of give us a blob, an elliptical. The other thing I want to talk about is over here. Again, we have our spiral on the bottom, we have our elliptical on the top, and in this case it's talking about density. Kind of density is always kind of how squished stuff is or how fluffy stuff is. So which one looks more dense up here between these two? The top one, yep. So if your protogalactic cloud tended to be both dense and non-rotating, okay, the dense ones would actually give us ellipticals. The sparser ones would be more likely to give us spirals. So we kind of have those 2 conditions. Rotating and sparse gives us spirals. Okay, non-rotating and dense gives us ellipticals.
Sorry.
I have things that go like that sometimes.
It's not even on, it's just going crazy.
Is that Siri?
I don't know what that was. Sorry.
So we could look at kind of the formation of galaxies to look like this. You can kind of see this wispy cloud, a little bit of contraction beginning. Again, now this is a cloud that's going to form a galaxy of stars. Okay, and this looks like it must have had kind of low density and rotation to give us a spiral. Now, one of the things we've been talking about galaxies is that they definitely interact with other galaxies. It's like I said, I struggle with this too, that Hubble discovered that all galaxies are moving away from us. Like, wait a minute, Andromeda's not moving away from us, it's moving towards us. So again, the exception being Andromeda is part of our cluster of galaxies. So we have interactions within clusters of galaxies. And so this is kind of showing you an interaction between a beautiful spiral and a cute little, another little galaxy minding its own business. By the way, what I'm going to show you starts with letter C, and actually this is on your test too. What do we call it? And I get so excited when there is like 2 galaxies coming together and one's really big, one's small. Cannibalism. Yeah, I don't know why that just tickled me. But yeah, this would be galactic cannibalism. Yep. And as they kind of interact or do a dance, we saw some photographs of kind of some neat sort of images of stuff flying out of here. You know, the mice take it's beautiful when galaxies interact. So this is just kind of showing you another way we can kind of get some maybe irregular galaxies or some kind of twists on, no pun intended, on a spiral galaxy, a larger bulge, is this kind of merging, in this case, cannibalism of galaxies. So this is one of the this is back to, those were figures, this is back to a photograph. So this is one of the interactions between two galaxies we looked at before. It's just very pretty. Okay, this is kind of showing you the dance from left to right. Here we have two spirals. So this would be source letter M. It wouldn't be cannibalism. It would be like banks do this. Galactic, source letter M. For the play charades. Businesses do this. AT&T wanted to blank with merge. Thank you. Yes, merge. Yeah, this would be more of a merger, and that's what you know, Milky Way and Andromeda is going to do. Yeah. So I think what I wanted to emphasize here is kind of see the second bullet, the second and the third bullet. When the universe was much smaller and those newly formed galaxies were doing their thing, and we see them kind of disturbed on their end, part of the reason they were so disturbed was the universe was smaller and there was more interaction, so they had more things to be disturbed about. They were getting disturbed by their closer neighbors than they are now. Okay, so this is just an image of a very distant galaxy. This is a picture that Hubble took of a very distant galaxy. Anybody remember, I think it's on the slide, the Spitzer Space Telescope? What wavelength does it look at? Not visible. It's IR. Yep, the Spitzer Space Telescope. So what your author's done is put together a little comparison of what we can see with the Spitzer versus the Hubble Space Telescope. This is visible. The caption says, finally mentions again this idea of redshift. What does redshift mean to you? Moving away, that's right. And how would you say if we have a galaxy A that's this far from us versus a galaxy B that's that far from us, which one's moving away faster from us? The B one, yep, the one that's farther is moving faster from us. So would it have more or less redshift? More redshift, exactly. And so kind of the deal of it then is, as we look back at those way far back in time at baby galaxies, they are moving even farther from us than the closer galaxies, so we definitely have redshift. Early galaxies, they just look like blobs. Not quite done, ready to come out of the oven yet. Now this is back to, yeah, that cluster of galaxies called Abel 2744. And again, if you know what you're looking for or looking at, they're kind of showing you location A and B here harbors these images. And these are actually the same image on the other side of the cluster of galaxies that are being gravitationally lensed. Okay. So now what I want to do is